plate tectonic theory account of the Earth is fascinating in itself, and also fascinating for what it reveals about the evolution of scientific thinking, of the thinking of a community of scientists over a period of 100 years in which we have several generations of scientists and their graduate students succeeding one another, and we get some feeling of the way that commitments to ideas and to theories can sometimes create tensions between those ideas and theories and accumulating data. It is not as easy as sometimes people make it out to seem, scientists themselves make it out to seem, that scientists are prepared at a moment's notice to adjust their theories to facts. What they will attempt to do is often to retain their theories in the face of what seem to be new facts that don't fit, by adjusting the theories or by re-examining the facts or denying that the data in question have the validity that requires them to change their theory. So plate tectonics, I think, because it's not mathematical for us, because we can describe it qualitatively, getting a feeling for what plate tectonics tells us about the Earth. What is the current, in the year 2000, what is the thinking of the the earth science community about the nature of the Earth is a worthwhile venture, because it reminds us, as I said in the last lecture, that Copernican revolutions do not just happen in astronomy. The idea of a Copernican revolution is a fundamental change in the way we think about things. So it is used metaphorically to refer to a fundamental shift in perspective. In the case of Copernicus, of course, it meant a shift in perspective from the Earth being the center of the universe to the Earth being just another planet rotating around the center of the universe, which is still pretty special, since the sun was conceived by Copernicus to be the center of the universe. But by the time we get to Newton, there's no center to the universe, and so that specialness is lost as well. But metaphorically speaking, then, any radical change in perspective that has sort of value connotations associated with it is called a Copernican revolution, the first term used metaphorically in this way, I believe, by the 18th century philosopher Immanuel Kant. So, because of that, I want to share with you a quick overview of what the Earth is conceived to be by Earth scientists as we turn into the 21st century. The core of the Earth is solid iron, at least 90% pure, at a temperature of 6,000 degrees Kelvin. This is comparable to the surface temperature of the sun. This is an astonishing amount of heat, which is largely residual heat from the formation of the Earth. Rock is a very poor conductor of heat. If you want to get rid of heat, conduction's not a good way to do it through rock. A much more efficient mechanism for transporting or dissipating heat is convection currents, which is sort of waves in which material can move and carry heat away from the solid core. The core, however, being solid, can have waves of current working through it, so the heat of the core can only get out of the core by conduction up to the edge of the core, to the limits of the core, which is 1,400 miles in diameter. The core of the Earth is a solid ball of iron under extraordinary pressure at 6,000 degrees. It is surrounded by a 1,400-mile thick band of liquid iron, obviously also under tremendous pressure, obviously also extremely hot, and that the heat of the core starts to become dissipated in the liquid shell that surrounds the core. The liquid shell that surrounds the core has convection currents inside it. So in other words, the material of the liquid iron is not smooth. It is roiled by these upwellings of liquid iron that form, in geological terms, storms within the liquid iron shell. It's almost as if they have weather patterns which can be detected using instruments that we have. We obviously can't look down there, but indirectly, again, through this global network of seismic sensors that have been put in place in the course of the 20th century, because earthquakes mean so much to so many countries, here's an area in which international collaboration is easy. There are tens of thousands of seismic sensors all over the earth, on the ocean floor, on continents everywhere, and they're linked together, and there's a very open sharing of this data, so scientists are able to build up, we'll talk about this, using a version of CAT scans that we know mostly from medical applications. The same technology builds up a three-dimensional picture of what the inner structure of the Earth is, and you can and scientists can see something like storms inside this inside the liquid core, which is trying to pass the heat of the solid core up and away, trying to get away, to speak anthropomorphically. So we have a 1,400-mile diameter solid iron core surrounded by a 1,400-mile thick liquid shell of liquid core. Above the liquid core sits the mantle. The mantle is 1,800 miles thick. I want to shift now to the surface of the Earth and get back to the mantle core, liquid core interface in a little while. But we'll start working our way down. The continents and the ocean floor I had already described are essentially rock and essentially rigid. The continents tend to be made of rock that is rich in silicon oxide, so they're called silicate rocks. The ocean floor, not surprisingly, now that we know how the ocean floor is formed and continually renewed, is basaltic. It's lava. It's essentially cooled lava. They sit on top of this not solid, not viscous material called the asthenosphere, which then sits on top of the mantle. The ocean floor material that gets pushed down, pulled down it sinks under the continents in the process called subduction, is, because it's cold, it's ocean floor material, and the average ocean temperature is quite low, that rock is cool. And as it gets pulled down, it is much cooler than the rock that it experiences in the asthenosphere, and certainly when it gets down to the mantle, even though it's being heated up, there's always a substantial temperature difference between the ocean crust that's being subducted and the material in the mantle, which is lava material. And so it sinks. Now, the mantle actually has, even though it's just it looks to the untrained eye like just an 1,800-mile thick mass of lava, actually has internally a barrier at about the 400-mile mark, so that the ocean crust material, by the time it gets to this 400-mile mark, which distinguishes an upper mantle from a lower mantle, it has melted, and it begins the process of circulating back up again. Some material, for reasons that are not currently understood well, some ocean crust continues down unmelted through the material and only, so to speak, completes its melting process when it hits the interface between the mantle and the liquid iron core. That interface is only about 120 miles thick, and it is considered by geologists to be the most dynamic and chemically reactive place on the Earth. Amazing that we can know that thousands of miles beneath the surface there is a 120-mile band separating the liquid iron core from the mantle. It is the most chemically reactive and geologically active, dynamic place on the Earth. And in fact, it is thought that it has a topography with mountains and valleys and stuff that would not look all that different if you profiled it from the surface of the Earth. What's happening here is that the liquid iron core has convection currents that are carrying the heat of the solid core up, but the liquid iron can't move into the mantle. So at that interface, the heat can only be transferred by conduction. It can only move across the liquid iron core mantle interface by conduction. That's a very weak, slow, and inefficient process. The amount of heat that does move up, and now we're going to start seeing sharp drops in temperature from that 6,000 degrees, we're down maybe in the 3,000 degree range now, in the lower mantle, that creates convection currents in the mantle, because the mantle stuff can move, unlike the solid core. And so you get these convection currents, which look just like patterns just like that, just like you would see in a pot of boiling water. And they are the ones that are carrying up the molten material. That's what's forcing them up, is the dissipation of the heat that the mantle picks up at the interface with the liquid core, where there's this 120-mile band that is extraordinarily reactive and interactive between the mantle material and the liquid iron. And the basic process of plate tectonics is that it wells up at the mid-ocean ridges. It doesn't come up anywhere else, and except for the occasional volcanoes. Those are often also associated with the same kind of activity. And we've already talked about how they push the continents apart. But there's a special case that I want to talk of that we've only become aware of in the last 10 years or so. And that is this material, the ocean crust that makes it past the lower mantle, upper mantle boundary and gets all the way down to the mantle liquid iron core boundary. When that happens, it creates what is believed to be a jet of mantle material. It's almost like as if it were a shock to that part of the Earth to have rock get down that low. And the stuff melts and goes squirting back up, where it comes out of the Earth as a hot spot, a volcano, or in the case of Yellowstone National Park, the hot springs and the and lava material that melt the mud and create. Now, what's interesting is, think of the plate tectonics theories. The continents are always moving, but these hot spots, they have nothing to do with the upwelling that causes the continents to move. They are because of a phenomenon in which ocean crust is somehow making it down to the mantle liquid iron core boundary. Those jets stay in the same place. So, as a matter of fact, what is now the hot springs, the thermal phenomena in Yellowstone, used to be in Oregon. And we can see the fossil remains of that activity, but the Western American plate has moved over a period of 100 million years, or tens of millions of years at any rate, far enough so that what was over Oregon then is now over Yellowstone. That jet stays in the same place. The continent moved above it. There are, in fact, numerous illustrations of this. There is a hot spot under Hawaii. Anywhere there's a volcano or a chain of volcanoes that are not above an upwelling of the mantle have to be above a hot spot. So, for example, Hawaii is no longer above the mid-ocean ridge, and the creation of new volcanoes in Hawaii is a reflection of a hot spot that is now. Hawaii is shifting. The Hawaiian Islands are moving in the Pacific Ocean, and so different regions are becoming above the hotspot, and that's what's going to cause a volcano to emerge in that place. And we actually can see this process. This is not a hypothetical process. A major illustration of it is less familiar to us here in America, but there is a region of India called the Deccan Traps, which is a vast, an enormous area of India covered by the remains of molten lava. What had been that once there were lava floods that covered hundreds of thousands of square miles of India. There is a hot spot that is now over Reunion Island. I'm sorry, yes, Reunion Island, that was once over the Deccan Traps. And at that time, it was much hotter and much more powerful. And so it created all of that. Now it's quieted down a bit, just as Yellowstone is not a volcano. Yellowstone's a hot springs and thermal phenomena, but it's not an erupting volcano, happily, at least not now, and hopefully not after this lecture either. But the Deccan Traps have moved on as India pushed its way into southern Asia. Right? And so the hot spot is now over Reunion Island. So this is an overview of a theory that has taken the Earth, an explanation of the Earth, and given us a picture of constant turmoil, constant dynamism, and even constant violent interaction. And we're now just talking about rock. We have to add to this, in the course of the 20th century, a deeper understanding of the atmosphere and of the oceans that required that we acknowledge that you can't just study the atmosphere without taking account of the ocean. You can't just take account of the ocean without taking account of the atmosphere and also of plate tectonics, which are affecting the oceans because of the nature of the spreading of the ocean floor, the effects of the mid-ocean ridges with their constant volcanic activity on ocean currents. Now, 20th century is the site of the serious study of the ocean because we didn't have the technology to study the deep ocean before we had submarines and research submersibles that could go down miles, that had the integrity, the structural strength to go down several miles and to observe what the ocean floor looked like. And so in the 20th century, we have come to understand, especially after satellites were put into place that monitored the Earth and the Earth's surface and the ocean as well as the land, that there were massive ocean currents, 50 million cubic feet of water per second. This is many times greater than the total outflow of all the rivers on the eastern United States and South America into the Atlantic Ocean. It's just an amount of water that is staggering. 50 million cubic feet of water per second move from the Antarctic region. This water is very cold, but it happens to be very rich in nutrients, in plankton material. It is very rich in nutrients. That water moves north, eventually reaching the Arctic regions where it sinks down and comes back in a constant circulatory pattern. But along the way, this amount of water, the motion of this amount of water, cold water, moving up to the surface and out from the Antarctic region, has a dramatic influence on weather and on life. In the wake of this current, there is a beautiful hierarchy of eddies. A wake, like the wake behind a powerboat. There is a hierarchy of large eddies and smaller eddies that you can see from space, that can be imaged from space. Of course, we couldn't see them down here. This is one reason why this is largely a 20th century science, late 20th century science. And these eddies churn the surface waters, and they spread nutrients, and they warm the cold waters, but they also cool the warm waters. This has effect on weather patterns, and of course it has effect on fish life and marine life generally. So these ocean currents are an example of how the underlying dynamism of the Earth physically manifests itself as energy that drives ocean currents that have tremendous implications for the atmosphere. I mean, we only learned about 30 or so years ago about El Nino, for example, but that's just one example of how ocean currents affect atmosphere, and they affect the biosphere as well, the life sphere as well. By the way, in the 1970s, we discovered these hydrothermal vents where the lava comes welling up out of the ocean, that around these vents there are dense colonies of new forms of life. In 1991, the research vessel Alvin, for example, actually observed an eruption in what's called the East Pacific Rise. And Alvin studied this eruption, and over time, as soon as the temperature of the molten material had subsided, life started to form. A dense colony, it wasn't created out of nothing, obviously, but creatures that had been whose peers had been killed when the eruption took place, creatures like that came flooding back in, and in a very short period of time, the area was densely colonized. What we have more recently than 1991 discovered is measured the temperature at which they start coming back, which surprised everyone because some bacterial life started to appear when the temperature was over 250 degrees. These creatures are now called hyperthermophiles. They really like a warm climate. This phenomenon, by which the underlying geological process is coupled to life, the fact that there are dense colonies, hundreds of new species and hundreds of new genera were discovered in the late 1970s and 1980s when we started pulling up from the ocean floor samples of the life forms, and then, of course, through research vessels like the Alvin that can take pictures down there, but actually pulling up what they call chimneys, these smoking vents that look a lot like chimneys that have cooled enough for life to cluster around them, pulled up the whole thing and seen how dense. These creatures never see light and they never experience oxygen. But they've been living there now. We have fossil evidence. They've been living down there for 3.5 billion years. So there is some question, and some people who think that life may well have originated not near the surface of the Earth, not in ponds, but that life may have originated deep in the ocean. And these creatures have a metabolism that's based not on oxygen, but on iron sulfide. Because the magmatic material, no surprise, is rich in iron. The magmatic material that wells up at the ocean is liberally laced with iron, which is the most abundant element in the Earth's makeup. And they use sulfur. Those creatures have evolved to use sulfur. They originated, perhaps, using sulfur as part of their metabolism, and the iron catalyzes the biological reactions in ways that we can study and replicate in the laboratory. So there's an intimate link to the biosphere right there. Atmospheric studies also changed dramatically in the 20th century. In the 19th century, I think I had mentioned earlier that John Dalton started his career as a physicist studying the atmosphere, trying to understand how oxygen, nitrogen, and carbon dioxide, three recently identified elements, in 1806 when Dalton published his a book proposing the atomic theory of matter. Dalton was trying really to understand. He was not a chemist, and he was not really interested in that chemical issue. Chemical reactions. What he was really interested in was the physical mixing of oxygen, nitrogen, and carbon dioxide. So atmospheric studies exist in the 19th century, but in the 20th century, because of our ability to study the atmosphere at multiple levels using aircraft, balloons, sounding rockets, and then after 1960 satellites, our appreciation of the atmosphere, our understanding of the complexity of the atmosphere as a system has increased by orders of magnitude. And in particular, I want to focus on one aspect of the atmosphere that is, even at the beginning of the 21st century, wildly underappreciated, and that is that the atmosphere transports between continents insects, seeds, pollutants, sand, bacteria, viruses. All of them are transported thousands of miles from Asia to America, from Africa to South America. But there is, depending on the wind patterns, there is a constant flow. When there is sand from China that routinely, from the Chinese desert, that routinely rains down on the west coast of the United States. And this sand carries with it bacteria and sometimes viruses. The world is interconnected in far more complicated ways than we like to think. You can't say this is where the United States ends and the rest of the world begins. The atmosphere, which is itself driven by the heat engines below and the heat engine from above, the sun, affected by ocean currents, affected by our own activity, is also integrating, is also linking the world in complex ways. And one realizes that you can't put up a barrier and say, pollutants released in India and Asia stop here. That, well, we're going to be good with our pollution. We don't care what they do. Wrong. what they do, and it doesn't matter who they are, if they release pollutants that reach the atmosphere, then that will be spread throughout the atmosphere in patterns that are sometimes difficult to predict. What is emerging here is, I hope, a sense of why, in the course of the 20th century, the systems approach to understanding phenomena became increasingly not just attractive, but almost mandatory. That it was necessary to think from a systems perspective, the way things are interconnected. Because what we've just been saying about the Earth applied also in the general theory of relativity and in quantum theory. That is to say, each of those theories told us about interrelationships that we had not appreciated before. In the case of the general theory of relativity, that space, time, matter, and energy are intimately interconnected. Even now, early in the 21st century, it is a controversy among physicists whether matter is a name that really belongs to the curving of space, or whether matter is what causes space to be curved. Which came first? It's a chicken and egg kind of question. But at a minimum, what we know from the general theory of relativity is that space, time, matter, and energy are intimately connected, and you can't talk about one of them independent of their influence on the other and the other influence on them. Analogously, remember we talked about the question in quantum theory about whether quantum theory violates the special theory of relativity's restriction on the transmission of information or a signal faster than the speed of light. According to quantum theory, especially now after the experiments in the 1980s of Alan Aspect have been replicated over and over and over again, the universe is interconnected at the quantum level in far more complex and subtle ways than anyone had anticipated prior to the last third of the 20th century. We don't understand yet the nature of those interconnections, but it's the sense of a system which is continually sensitive to the relationships among all of its elements, even, apparently, in violation of the restriction of the special theory of relativity. So that you can change something here and have an instantaneous adaptation over there, as in the case of the entangled photons that I described in an earlier lecture. So the notion that the Earth is a system becomes a fundamental theme in late 20th century science. And of course, in earth science, one of its manifestations was the environmental movement. And within the environmental movement, the notion that we have to recognize that there is no single aspect of the Earth that can be treated in isolation. That you cannot say, I am only polluting locally. You cannot say that I will do my thing and not worry about the impact of others on me or my impact on others. We saw this in the case of the ozone hole, which was quite an extraordinary social phenomenon as well as a physical phenomenon. That is to say, the reaction that, well, we really are destroying the ozone. And the ozone, which from the 1920s had been appreciated as a barrier, happy barrier, between us and ultraviolet radiation that is extremely harmful to life, and at our stage of evolution, highly mutagenic, is certainly associated with skin cancer, but at the level of plants, for example, would have devastating consequences for agriculture. The reaction to the ozone hole, that we actually stop producing CFCs, and that maybe the ozone hole will repair itself, the evidence at the moment is unclear, is one illustration of an eruption of systems thinking into the public consciousness. We are currently experiencing a second eruption over the whole question of global warming. Is it the case that human activity has either caused or is intensifying the warming of the atmosphere, which is an empirical fact? No one can deny that. The only question is whether we're contributing to that, or we can say, well, our emission of carbon dioxide gas is negligible, and so it is of no consequence. We are wrestling still with the complexity of acknowledging that we're in a relationship, and most of us feel much more comfortable with being able to uncouple and say, it's just me. When you're in a relationship, your obligations and your behavior is much more complicated than when you're not, whether it's a social relationship, personal relationship, or when the kind of relationship we're talking about is the relationship of the elements of the Earth to one another. And by element here, I don't mean atomic element, I mean ocean, atmosphere, and Earth. What we need to look at in the next lecture is the notion that the Earth itself is only one node in a much larger network, much larger system which extends extraterrestrially.